Thus far, we have looked at vectors in just two dimensions. We've had the x-axis and the y-axis, and we've looked at vectors in the xy plane, in that plane. Well, it doesn't take a whole lot to expand our discussion to what we're going to call vectors in space, where we have the xy, and then we have the z-axis coming out like this. So here's the z-axis. So think of the xy plane as maybe a table, and then there's a stick sticking up from the middle of the table. That is the z-axis coming out of that plane. And when you do that, you get other planes, right? You get the plane, the xz plane, the yz plane, the xy plane. In other words, you have now points in space that you can identify. But when you're just dealing with two dimensions, x and y, you have ordered pairs. When you add that third dimension, you have ordered triples. So in other words, we have points like this, -2, 5, and then the z coordinate, the 4. So the way we would plot that point is to go over on the x to a -2. So this is the x-axis right here. The y-axis is here. This is the positive y's over here, negative y's over here, positive x is here, negative x is here, and then the z's, positive z's up here, negative z's down here. So if you wanted to plot -2, 5, and 4, you go to -2 on the x, then you go up here to 5 on the y, and then up to 4 on the z, and you get that point right there. So that's the way you plot these ordered triples. Now the thing is, we're not going to get too involved in the plotting of these points. We just want to, while we're talking about vectors, let's just go ahead and throw in the third dimension. So what I want to look at is, we've got this -2, 5, 4 here. Well, you could easily say, okay, we could talk about a vector going out where that's the terminal point, and we could talk about a vector, maybe, maybe we could talk about a vector. I'll name it maybe vector u would be -2, 5, 4. Okay. 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 So we could talk about a vector in 3 space, right? Not just 2 dimensions, but 3 dimensions. So there we have that vector. We have these other vectors here. Maybe we have a vector pointing out here. See? All these vectors. And all that we know about vectors in 2 dimensions, we can expand to vectors in 3 dimensions. For example, let's suppose you've got a vector that has a terminal point. Okay, we have a terminal point, an initial point here at P, a terminal point here at Q, and we want to put it in component form. Well, we do this the same way. I'm going to take the x components, subtract those, the y components, subtract those, and the z components, subtract those. See? And then we get a vector that has an initial point at the origin and the terminal point out here, maybe v1, v2, and v3. So let's take a look. Let's suppose we've got a couple of vectors. Or let's suppose we've got a vector, let's say we've got a vector, and this is in 3 space. We've got 4, 2, and 3. That vector, and then we've got another vector in 3 space, which is -1, 5, and 6, let's say. Now, all that we know about vectors in 2 space, we know about these. So in other words, we could say u plus v. Well, we just add the corresponding components. So 4 and -1, that's 3. 2 and 5, that's 7. 6 and 3, that's 9. Yeah, see? And we could also subtract if we wanted to. Now, we could also do scalar multiplication. So I could say 4 times u. Well, that's going to be 4 times the u vector. And that's going to be, what, 16, 8, and 12. See? Just multiply it. We could talk about the magnitude. Maybe the magnitude of v. and that's going to be the square root of negative 1 squared plus 5 squared plus 6 squared. Okay, so what would that be? That would be 1 plus 25 plus 36. And that would be, I believe, the square root of 62. So, okay, so the square root of 62. So we can get the magnitude. Now, also, we could write this as a linear combination. But, and recall with the linear combination, we have the I vector, which is 1, 0. But now that we're adding another component, another dimension, we have to put something for the z. Remember, we have the j vector, the unit vector, and that's going to be 0, 1, 0. But now that we have the third dimension, we add a k vector, a unit vector, and that's going to be 0, 0, 1. So if you wanted to write u as a linear combination, a linear combination, well, that is going to be, okay, so here so that's going to be, let me see here, sorry. What we have is, it's 4, 2, 3, so that's going to be 4i plus 2j plus 3k. There we go. So there's our linear combination. Now we can also, of course, do a dot product. So that's going to be 4. We just multiply corresponding components. So this is 4 times negative 1 plus 2 times 5 plus 3 times 6. Okay. So that's going to be negative 4 plus 10 plus 18. Yeah. See, I just multiply each one of those. Negative 4, 10, and 18. Then we add those together, and let's see what we get. We get negative 4 plus 28, and I guess that's going to be 24. Yeah, so we get our dot product. But this is how we can deal with if we have vectors in 3 dimensions. Now we're not going to put it in trig form, but we can put it in linear combination. So pretty much everything is the same, except we have another component to deal with.